Hey everybody, I'm back from Computex, and I managed to sneak out an MI300. Not really, but I mean, kind of, sort of. Let's talk about the MI300A. This is not a 300A. This is a 300X. 300A, 300X, x86 cores make the A. The A? The A. This is not actually a video about the MI300A. This is a video about what I saw with Nvidia's Grace Hopper and unified system architecture, and maybe some writing on the wall for software developers. This is really about the software experience, or maybe the ecosystem experience, but there's kind of a lot of things we can touch on, and I have questions, but also I want to share my thoughts. So let's dive in. The MI300A, this chip is a bit unique because AMD has integrated x86 cores directly into the GPU, and it uses HBM memory, so it's a bold move. And I see it as part of a broader trend toward unified system architecture. Or maybe it's going to be an experiment that goes down in history as legendary, because it is absolutely a legendary piece of hardware, but never actually takes off. We can see similar efforts from Apple with their M series. It's an ARM architecture. It's an ARM CPU under the hood, but maybe x86 will win in the end? I don't know. I mean, I was surprised that Nvidia's Grace Hopper superchip is more or less the same system architecture as an x86 server loaded with a bunch of GPUs. If you look at the diagram from Nvidia, which we're going to refer back to a bunch in this video, okay, I mean, it's really not that different. It's not a dramatic change. I think some of the changes that we see from the MI300A may indicate that we're nearing an inflection point in the industry. And the more I peel back the layers on Grace Hopper, the more I see evidence that there is some architectural inflection point stuff like I'm talking about in Grace Hopper, but the block diagram doesn't make that super obvious. What I'm talking about is how we approach computing at scale, and really how developers are expected to interface with that. I mean, there is a little bit of a catch here. The hardware innovations are here, but the software is maybe the part that's not quite here yet, or maybe it's in a transitional phase, or maybe some of the server design papers over some of the architectural changes. And this is all things that I find very fascinating. You really need to think outside the box with system architecture and disaggregation of hardware for our infrastructure as code future. But I think some of what has driven NVIDIA's choices here, and some of the larger choices in the industry, even from Open Compute, is around the software development experience and making it to where developers don't have to worry too much about it, which is also not great because a lot of performance can be left on the table by that. Like, developers get it working, and they don't, like, developers that can also do optimization are much more rare than just developers. So for those of you in software development, pay attention, I think, or ask me questions, or give me stuff that I'm not necessarily thinking about. This trend toward unified system architecture or unified memory architecture could significantly impact your work. And what I'm talking about is making it so abstract that what is GPU memory and what is CPU memory basically doesn't matter. Some of that in Grace Hopper doesn't necessarily have to do with the fact that it's not technically a unified system memory architecture. I mean, okay, actually on the GPU side with the NVLink thing, you could say that there is a unified architecture thing going on there, but just by virtue of the fact you can link 256 GPUs together, but that's not the same thing as system memory and GPU memory being linked together. System memory is slow, GPU memory is fast. And as a developer, if I can have both slow and fast memory, that's what makes the computer go. That's the whole, like, having small amounts of insanely fast memory and large amounts of slower memory in tiers is what drove the entire computer revolution since the dawn of time. And we have an opportunity to do that here, and it is in NVIDIA's hardware. I'm getting ahead of myself. Bottom line, NVIDIA's stock is so insane precisely because of the promise that the system architecture is not going to change that much. And the promise is to developers. The developers are going to experience a software ecosystem that from their perspective basically won't change. And this rack scale ball of wires, this cabinet signed by Jensen himself that we saw at Computex, is going to present to you, the developer, as a single GPU. We saw these cabinets from Gigabyte and MSI and ASRock and Supermicro and METAC. Literally anybody who has the capability to make a server chassis is making bank with Nvidia because they cannot make these fast enough. This is their system architecture all the way from the Grace Hopper superchip all the way up to the NVLink interconnects and even things beyond rack scale. It really is wild, like, how much money Nvidia is spending having these things built as quickly as possible. Now check out the block diagrams provided by Nvidia developers for the Grace Hopper superchip. The Grace CPU supports up to 512 gigabytes of LPDDR5X, while the Hopper GPU can handle up to 96 gigabytes of HBM3. The interconnect speeds here are impressive. The GPU can connect directly to the Grace CPU or up to a network of 255 other Hopper GPUs at 900 gigabytes per second. However, the GPU memory interface, that's the star of the show, 3 terabytes per second. That's that HBM3E. Notice the CPU interconnect is just over a tenth of that. Even our DDR5 memory interface is plucky by comparison. Now, also take a look at the physical stuff for this system that I saw at Computex. They're moving all the complexity onto the CPU and GPU packages themselves. I mean, the superchip is relatively small here. It's tiny. This complexity is all around the interface, and this system does have a mix of LPDDR5 and HBM3E, slower system memory and faster system memory. That's sort of what I'm talking about. Contrast this to Apple's M architecture, M1, M2, M3, M4. Those chips have on-package memory, but largely Apple hasn't taken advantage of the performance benefits that can be conferred from having on-package memory. It's mostly power savings that Apple has focused on. And yet, as I'm sure that the comment section will attest, the folks that shelled out for the 96 gigabytes of memory and beyond Apple laptops, oh, you might have overpaid there, sorry, are able to run large language models because of the unified memory architecture. CPU memory, GPU memory, there's not really a distinction because it really physically is the same memory. And so Apple was, ARM really was basically able to just say, hey, let's just not move things around. It's not terribly fast, but it does work, and it is generally a better experience on PC. But it's a unified memory architecture. Nothing has to move between memory because the memory is literally the same. And part of the reason the performance is so good is because Apple's memory controller genuinely is really good. It doesn't have a bottleneck, and the caching system is quite good on the Apple ARM M architecture. And so it is a pretty reasonable experience, even given that it's only LPDDR5, and best case scenario, you're not going to be anywhere near the bandwidth of like an HBM type solution. So we're talking about a memory bandwidth that is at best, 25% less than what you would experience on the Nvidia CPU ARM side of it. Now, Intel's Lunar Lake and AMD's Hawk Point are trying to make this unified experience more feasible on PC, mainly driven by NPUs, like their neural processing unit. It's still a work in progress, of course, but part of the idea with resizable bar and making the NPU driver architecture based on WDDM in the case of Intel is to try to better leverage access to data in the context of a GPU operation or CPU operation or NPU operation to just make it a memory operation, because it's all the same memory at the end of the day when we're talking about a portable system. At least one that doesn't have a discrete GPU. Now, let's bring that back to the MI300A. It's x86 cores, but the memory is on package, and it's HBM3E. So the x86 cores are fed by this absurdly fast HBM3E memory, but x86 cores aren't really designed for that. Patrick at Serve the Home did a really nice expose on the Intel Xeons that have HBM2E. He got his hands on those and was able to do a deep dive. And honestly, I was expecting a lot more insane killer stuff to come from those. It hasn't really materialized. You could run those Xeons with only the HBM2E memory or with interleaving, or you could take over in software and have the software do caching and fun stuff. I'm sure there's specialty software out there that now depends heavily on those CPUs, but in terms of like the entire world is beating down your door to get those CPUs, not so much. And it would seem to be the case also with the MI300A. Now the MI300A, does it seem like the MI300A systems are disadvantaged with no DIMMs? There's nowhere to physically add memory. I mean, that might be a disadvantage, but also CXL might bridge the gap. And so this is a little bit of a background to say, hey, CXL could thread the needle for AMD customers and Nvidia customers both. Now, Nvidia is not going to like that CXL can thread the needle, and so this is the part you should pay attention to. But I think that CXL as a way of expanding memory beyond HBM3E could also be an interesting thing for AMD to do strategically. Like if AMD enabled better CXL functionality, it could also kneecap Nvidia in a way that they frown upon. Let me explain. CXL, or Compute Express Link, has been in development for a while. It's really cool in that it enables whole new branches of computer science for managing information and continuity in the case of failure. You can have a CXL device shared among multiple physical hosts. The database people were really excited about this for being able to use CXL devices for ACID compliance and transaction log save and replay. And it really does unlock some new computer science there, because you're assured that the transactions make it off of system to another system, but it's also low latency, high speed, high coherency. And AMD's done a lot of strategic acquisitions for interconnect companies, FPGAs, and, Pensando, and all of this goes together, but is getting a little beyond the scope of what I want to talk about in this video. Just know the CXL is high speed in terms of it looks like a PCIe Gen 5 device. It's the latency of PCIe Gen 5, and so it's high speed. But when I say high speed, you should think of high speed in the context of that Grace Hopper diagram, where the numbers on the left are like, okay, but then you got 3 terabytes per second on the right. It's like, that's a whole other ball game in terms of speed. What if there existed a CXL device that would allow you to expand the HBM memory? Okay, yeah, I mean, the PCIe speed's basically the same as a memory controller. You're not really at a terrible speed disadvantage when we're talking about native DDR5 memory channels. You're just at a disadvantage when we talk about HBM2E. What if this is a way for Nvidia customers to expand their VRAM? That could be interesting. That was another thing that I looked for at Computex. Now, keep in mind that Nvidia offers different configurations of Grace Hopper. You can get dual Hopper and no CPUs, but it seems like in Nvidia's architecture, they're saying, 500 gigabytes of, low-cost DDR5 to just shy of 100 gigabytes of HBM3E. That's the good ratio. We can feed it. Like that set of memory tiering, we'll handle that in software. Developers won't have to worry about it. It's going to make a lot of sense. If Nvidia can get done in 96 gigabytes of HBM3E, what will require AMD to use 128 or 288 gigabytes of HBM3E, that is actually a competitive advantage for Nvidia. But I think the reality is that the customers, especially the open compute customers, just want an absurd amount of the fastest memory you can get, because all other variables don't matter that much, which is interesting. Now, the one shining star at Computex in this thread of thoughts rattling around my brain was Fison and their adaptive solution. This is not DRAM, and it's not CXL. They're using NVMe, PCIe over NVMe. GPUs can talk directly to NVMe. Some of the plumbing and stuff is there for that on the Nvidia side as well. And with Fison's adaptive solution, they're able to take single-level cell NAND flash and basically use it as a second tier of VRAM, even with NVIDIA-based GPUs. So if you need to do a job that requires a terabyte of VRAM, but you've only got 4 A100s that have, 320 gigabytes of memory, you can make up the difference by throwing in some Fison high-performance NVMEs and Fison software, and the software will be like, PyTorch or whatever will be able to run and get that done like as if you have over a terabyte of VRAM. This is a really interesting product, so it can be done. The other thing to look for at an operating system level is, does your operating system have a concept of things like you have fast memory and slow memory? And just a couple of years ago, the answer to that was no. But the Linux kernel has actually gotten support for more of these memory performance tiers. Not only that, they've gotten really good support for things like NUMA nodes that don't have local compute but only have memory, or that have local compute but no memory, because that was the thing with 2000 series Threadripper. That's a video for another day. But the fact that Linux support for that has become first class tells me that there are enough customers out there that are working on this kind of thing that yeah, we could actually see systems that take more advantage of fast HBM3E and slow DDR5. Presumably Nvidia has that in their software stack, but is proprietary probably and not open source and blah, blah, blah. So it's really nice to see that on the Linux side because people will be able to take better advantage of that. That also means that CXL devices plus an MI300A should just work out of the box because those Zen cores should support CXL. Maybe it's an IO die kind of a thing. But if there was a 1 terabyte DDR4 CXL module out there, then boom, that may be you're immediately good to go on your MI300A based system, and you don't have any of the disadvantages of being locked into only HBM3E memory. Don't know. I think also based on the comments that I heard at Computex, with Nvidia spending so much money with so many partners, I think if Nvidia says, I don't know if we want to qualify a CXL device on an Nvidia-based solution, sorry. That could negatively impact how quickly we see a product like that come to market that's Nvidia compatible. Meanwhile, it's in AMD's advantage to bring such a product to market, not only for the MI300A, if they're interested in the MI300A, but also to ensure that less NVIDIA GPUs get sold, possibly, maybe, in some parallel universe. I mean, okay, possibly. The other variable here is open compute. So open compute is, Meta, Facebook, Amazon. They dictate the hardware because all the hardware companies were playing games with how you were selling lots of hardware to hyperscalers. And so they've gotten to the point where they specified down to the chassis. Their engineers are very good. They're doing a lot of optimization. The thing that I'm worried about is that I haven't seen quite as much involvement of open compute on the software side of it. I'm sure that the software engineers are whispering into the hardware engineers' ears. No doubt about that. But if you look at the meeting minutes and some of the open compute get-togethers, Google and Meta and Amazon are very, very cards close to the chest when they're talking about their software stack and what their software needs in terms of enablement. I'm sure that they share with partners like AMD, hey, this is the software they're working on under the hood, under an NDA, of course, but that is not something that is really super openly discussed in those open compute meetings. And I think that's putting the open compute members at a disadvantage because you possibly miss solutions like, oh yeah, we could just use CXL to expand our VRAM space, maybe, or some other PCIe type storage to expand our VRAM space, maybe, and solve some problems that we have immediately versus waiting for the next hardware engineering cycle. We also haven't really talked about how things that are far away increase latency, and latency management also enters the equation here. I mean, if you look at the physical design of NVIDIA's racks, they're putting all the fabric communication gear in the middle of the rack. That's not for aesthetic reasons. That's because we need to minimize the signal propagation delay problems, because speed of light, it's a real bitch. So yeah, latency also factors in here and making the fabric as low latency as possible, and there's some stuff that goes with that. CXL has some stuff in it for hiding latency and doing coherency after the fact, which is, again, black magic in terms of computer science, but it's exciting because it's also new computer science. So anyway, to wrap this up, this is something that I wanted to be on your radar. Unified system architecture, but also like software that can properly leverage fast and slow memory is a thing. And software that can properly leverage fast and slow memory unlocks a whole new set of possibilities without having to have a terabyte of HBM3E on every GPU. I don't think we really need that because we can't process that quickly. But this kind of is an inflection point. And the inflection point is happening on mobile because unified system architecture on mobile saves power and just makes sense. And so it's weird because for the first time, instead of data center technologies trickling down to the consumer, there may be some consumer software technologies that trickle up to the developers running in the data center, at least in terms of taking full advantage of a unified system architecture. And then maybe it would make sense to have systems running on HBM3E, because right now HBM3E in like a notebook, you would expect that to be amazing, but it's just not. It's just not in the same way that those Xeons with HBM2E was not really amazing for most things. It's just not. Most people don't realize, but Nvidia has been working double plus overtime to ensure that developers don't actually feel the changes under the hood that exist with Blackwell and their next generation platform. That also ties into that promise that I was talking, like line go up as long as Nvidia makes all of this transparent to the end user. And that is 90% of the reason that Nvidia has gone up the way that it has, is their software moat. If they fumble this in the slightest, they're going to lose some of their grip on their development ecosystem, because under the hood they had to make some changes in order to better address latency and scalability and everything else. And Nvidia sees the solution as lots of GPU in a distributed pool with very low latency, and so you get the best of all worlds in terms of an enormous HBM3E memory space, because you don't have information duplicated across GPUs and everything else. Outside of Nvidia, in the broader software ecosystem, I think the rest of the players do still need to play a little bit of catch up here. And I think part of that is because the open compute players are not wanting to work together all that much on the software, because they want to maintain their individual competitive advantage. They're really just not eager to share their software special sauce. And this maybe puts AMD and other participants in open compute at a disadvantage, because does it mean that AMD has to solve these software problems? And does it have to solve these software problems in a way that thread the needle that is not going to piss off their enterprise customers? I mean, the MI300A could be the most amazing, interesting way to run their AI workloads. And AMD has gotten some major wins through open compute with ChatGPT. I mean, you realize that ChatGPT is running on Instinct systems from AMD. I honestly don't know if CXL would help with MI300A adoption. It seems like MI300A should be, something that's really innovative, but we didn't hear anything about it at Computex. And it could be that the MI325X or, the MI300 successors are just going to overshadow the MI300A. I mean, Nvidia's design with Grace Hopper is basically the traditional, we have a crap load of DDR5 tied to the CPU, and we've got the really high-speed HBM3E, and the CPU is going to have to move things in and out, and that's just the overhead that we're going to have to deal with. Maybe that's what it looks like in the real world. But consumer devices that have one block, it doesn't make sense to have a laptop with 32 gigabytes of DRAM and 8 gigabytes of VRAM. Like, you should just put all that together, and the operating system should look at it and say, okay, I should use the high-speed VRAM for the game the person is playing. And when the person is not playing a game, then we can use the high-speed VRAM for the operating system. Like, that should just be part of the hardware architecture. But that is way, way easier said than done. But it sure does look like consumer devices are going to drive some of that innovation that may trickle back up to the enterprise and make things a little easier on the enterprise. When we step back a little bit and we talk about, disaggregated hardware, and you have a pool of compute, and is it CPU type compute? Is it GPU type compute? What are your containers needs? I think my next step, there's a certain company out there that is doing some really wild stuff in terms of putting a pool of x86 resources together in a high-speed cluster. How about a server without a BIOS? Because the BIOS is too slow. Turn the CPU on, feed it the Agiza, add it to the network, and done. That's a future after my own heart, and likely a future video. I've got to get out there to go see them soon, and I think that some of the threads that I've started to pull on in this video, we can pull on in some different ways in that video. So I'm trying to work that out, and be sure to look for that. But yeah, just some thoughts on where was the MI300A at Computex, but also how is Nvidia presenting to developers something that's like a unified architecture, but under the hood is in fact not? And is that a portent of things to come for our unified ARM architecture future, where the GPU does have fast and slow tiers of memory? I don't know. I'm Wendell, this is Level 1. I'm signing out. You can find me in the Level 1 forums.